Hi everyone, this is Mr. Zikri speaking. Today we are going to study about Faraday's law. Here on the slide we have some picture showing a bar magnet is being held by a hand, and then there is a loop here, wire connected to ammeter. So here, as you can see, magnet bar has electric field lines that is going from north to south. These electric field lines that going through this area is called actually magnetic flux. Magnetic flux. Magnetic flux is magnetic field lines times the area times cosinus the angle between them. So this is magnetic flux. So this magnetic field lines is actually we call it magnetic flux. Now if we move the magnet bar toward the loops, as you can see, the number of the magnetic flux going through this loop is increasing. When this magnetic flux is increasing inside the loop, it is created current, and then it is detected in this ammeter, so this indicator going to the right. Normally it will stay like this. So when we move this magnet bar toward the loops, it will create current. It is called induced current, and it is creating EMF inside the loop, or electromotive force. So from this picture we can say that if there is a change in magnetic flux, if there is a change in magnetic flux, inside the loop, there will be EMF and electric current. So I'm going to underline this, a change in magnetic flux. So if there is no change, is there EMF or electric current? Yes, the answer is of course no. From the second picture here, when the hand is stopped moving, when the hand is stopping to move, so there is no change in magnetic flux here inside the loop. So this ammeter reads nothing. The indicator will not move to the right or to the left. It will stay right there. So again, there is no change in magnetic flux. Because of that, there is no EMF and current. Now the third picture showing you that if you move this magnet bar away from the loop, as you can see that the magnetic flux will be decreasing here inside the loop. Because it is decreasing, that means there is a change in magnetic flux. Also, it will create EMF inside this loop, that is creating current. That is opposite with the first condition. The first condition, the bar magnet moving toward the loops. The third condition, the bar magnet moving away from the loop. The current created is opposite. So that is the basic concept of Faraday's law. If there is a change in magnetic flux inside the loop, there will be EMF and electric current. Okay. It will be very interesting if we know the application of this Faraday's law. So some of you may be what is it? Hobbies. Your hobbies may be playing guitar, for example, like electric guitar. How do you convert this sound into electrical data, or what is it, and then it will create sound in sound system. So it should be converted into electric signal. So here an example of application of Faraday's law. As you can see here, we have electric guitar. So there is a device here, we called it the pickup. So this pickup actually what is it? A metal that is being covered with the wire. So it will create north and south pole on this metal. So it will create electromagnet. And here is the wire. This is the wire one, bus, and then this the smallest one. And if this wire is being struck and then it is moving, yeah, it will change the magnetic field near the coil. So it will create electric current. So it will induce electric current. This electric current then amplified to create the sound of electric guitar. So because of this, around this, it will, if the coil is moving up and down, it will create a change in magnetic field. So when this happens, it will create induced current. So that's how you change sound, like mechanical sound, into electrical signal. So you change the magnetic field around the wire. Next, so I want to show you the mathematical expression of this Faraday's law. Here we have EMF. So EMF created inside the loop, or induced EMF, is actually delta magnetic flux times N over time. So if there is change in magnetic flux over time, it will create EMF. What is N? N is number of the turns on the wire. So if you make the turn is only one, you don't need this N. But if you turn the wire more than one, so you need this to multiply it, this change of magnetic flux. Actually, it should be negative. So what is that mean? This negative sign is actually showing you the direction of induced current. It will oppose the change of magnetic flux. So, for example, I'm going to show you this. So, this one is front. So you can, this is what is it? Behind, yeah. So first of all, the magnetic is here. So let's say this. So if it is moving here with velocity v, the magnetic flux that going through this wire will be increasing, right? So it is because increasing, it will oppose the direction of the increasing magnetic field. It will create the direction here, like clockwise. So if it is increasing, it will be clockwise. If it is decreasing, it will be counterclockwise, something like that. So here is more on Faraday's law of induction. Change of magnetic flux through a loop induces EMF and therefore the current in the loop. So magnetic flux can change in three ways. First, field can change. So if there is a magnetic flux increasing, going into this loop, so it will create induced current. Yeah. The second one, theta can change. So if we have this coil like this, and then it is moving in a rotational way, it will change the theta. That means the angle between area of this and the magnetic field changing. And the third one is the area. If I want to write down all the things, EMF actually equal to minus n delta flux over time. As we know that flux is actually magnetic field times area times cos theta. So here basically you will have several variables that can be changed to create EMF, induced current, magnetic field, area, and the theta. Next, an example here. A coil with 25 turns of wire is wrapped around a hollow tube with an area of 1.8 meters squared. Each turn has the same area as the tube. A uniform magnetic field is applied at a right angle to the plane of the coil. If the field increases uniformly from 0 Tesla to 0.55 Tesla in 0.85 seconds, find the magnitude of the induced EMF in the coil. If the resistance in the coil is 2.5 ohm, find the magnitude of the induced current in the coil. So we have the number of turns and we have the area of the hollow tube, and then we have the initial magnetic field and the second condition of magnetic field over time. And then we also have a resistor here, 2.5 ohm. Yeah. How do we find EMF? It's easy, right? So I'm going to write down all the given variable. The N is 25, and then the area is 1.8 meters squared, and then B1 is actually 0 Tesla, and B2 0.55 Tesla, and then the time 0.85 second, and given the resistor 2.5 ohm. So let's solve this. EMF is minus n delta B A cos theta. Oh yeah, the angle between B and A is 90 degree, and then we know that it's the right angle with the area means it has with the plane, actually the theta is actually 0, so we have that cos theta is 1 over time 25 delta B. So because B is changing, B2 means 0.5. Okay, here what is changing is actually the B that is changing, minus 0. A is the same of times cos 0 over time is 0.85. So what do we get here? I'm going to use this calculator. 25 times 0.55 times 1.8 equal over 0.85, and we have 29.1 volt. And what is the current? So the current I is EMF over R. So we have in this current I 29.1 over 22.5. Yeah, 29.1 over 2.5. Okay, the current is 11.64 ampere. So please again, my beloved student 11B, pause this video and then write all the things that is written in this video, and then if you have already done it, we are going to continue to the next slide. Okay, I'm going to continue to the next slide. Here, as you can see, first of all, there is a magnetic flux going to this loop, and then at condition B there is a change. Yeah, so inside this loop it will be created magnetic field, EMF and induced EMF, So if there is magnetic change in magnetic flux from 4 into 0, so it will be decreasing, it will create EMF inside the loop. Okay, so from 4 to 0, so there is a change in magnetic flux. Inside this loop there is a current, induced current. Next, the conducting rods are moved on the frictionless rail as shown in the figure, in which resistor is or are an induced current formed. Look at the first condition. This is the area of the loop, and then this bar is moving to the right, and then this one moving to the left. So this area is actually decreasing. Because of area decreasing, the magnetic flux inside this area also increasing, right? So here it will be created EMF, induced EMF. And then the second one, as you can see that if these two bar moving to the right, there is no change in area, there is no change in magnetic flux, so there will not be a magnetic flux. The third one, if we move this to the right, as you can see, if it is moving to the right, the area of the loop will be increasing because this wire is not in a parallel condition, it has an angle to each other, so it will be greater area. It will become a bigger area when these two bars moving to the right. So there is two condition that will create EMF, induced EMF here. Next, in which of the following system can an induced current be produced? Here, of course, if it is moving in circle, it is having rotational motion, it will create it will make the angle theta changing, so it will create EMF. The second one, this magnetic bar is moving to the right, so it will also create EMF. But the third one, it cannot, because when this loop is moving to the right, the number of magnetic flux inside this will not change. As you can see, there is no change in magnetic field strength, and then there is no change in area. So 1 and 2. I'm going to check. Okay. Here is the final one. We have a loop here. Yeah. We have B going away from us or into the paper. We have the area here 0.5 meter square, and then the resistor is 5 ohm. The magnetic field is increasing from 2 Tesla to 12 Tesla in 0.1 second. First, find the EMF. It's easy, right? EMF, or you can just write E equal to A, because it's only one loop. You don't have to write N. Delta B times A over time. So 12 minus 2 times 0.5 over 0.1. What we have here is 10, 5, 50 volt. And then what is the current? Current is EMF over resistance. EMF is 50 volt over R, here 5 ohm. So we have 10 ampere. Okay guys, that's all for today. We're going to continue to study to the next topic in the next video. Thank you. Have a nice day. Assalamualaikum warahmatullahi wabarakatuh.